everyone! Welcome to part 1 of chapter 7. Today we are going to discuss how to use those intermolecular forces that we learned about in chapter 6 to identify different types of solids. So let's get going. Okay, so we have two different types of solids. We have ionic solids and we have molecular solids. Just like we had two different types of compounds. We had ionic compounds and we had molecular compounds. So ionic compounds will make ionic solids and molecular compounds will make molecular solids. So don't make that harder than that needs to be. All right, let's talk about each one. So ionic solids, most ionic substances, just in general, are solids at room temperature. So let's think about a really common example, like table salt. Table salt is a solid at room temperature. Table salt is NaCl, and we recognize that this is an ionic compound because it has a metal and a nonmetal. So an ionic compound will make an ionic solid. And again, most ionic compounds are solids at room temperature because of the strength of the forces that hold them together. Last time we learned about intramolecular forces and intermolecular forces. Intramolecular forces, we said, were bonding forces. And remember, at the very, very, very top of the strength chart, that was ionic, right? Ionic bonding is the strongest intramolecular force. So because that force is so strong, it's essentially locking those atoms and molecules into place. So ionic compounds have the strongest intramolecular forces, therefore they are likely to be solids at room temperature. Also, they make a highly ordered three-dimensional array of alternating cations and anions. So if we were to kind of zoom in and look at atomic level, we would see, okay, a cation, anion, and so forth. And then the next row would alternate. Anion, cation, over and over and over again. Okay? And so it's a very, very, very ordered structure. Molecular solids are a little bit different than our ionic solids. Remember, molecular solids are going to be made up of molecular compounds, like water, for example. And we'll recognize that this is molecular because it's made up of all nonmetals. So all molecular solids also have dispersion forces, okay? All of them, polar, nonpolar, doesn't matter. All of them have dispersion forces. But the ones that are polar also have dipole-dipole or hydrogen bonding, okay? Remember, we said that polar substances had dipole-dipole interactions because the dipoles are what's making them polar, right? And then if it was a hydrogen bond, the way that we recognize that is it would have a hydrogen that was bonded to a really electronegative atom, fluorine, oxygen, or nitrogen. And remember, I told you hydrogen bonds just want to have fun. So molecular solids are held together by dispersion forces and also sometimes dipole-dipole interactions or hydrogen bonding. Okay, so these though are weaker intermolecular forces than our ionic solids, because ionic compounds are going to have the strongest forces holding them together. So molecular solids will have weaker interactions than our ionic solids. Okay, so we have two different types of solids that can happen. One of them is a crystalline solid. So a crystalline solid is going to be a highly ordered structure, like I was talking about with that ionic compound. Ionic compounds always make crystalline solids. So ionic compounds are always crystalline. Okay? Molecular substances are usually crystalline, but they can also be amorphous. So amorphous means without form. Okay? And so it's not going to be a highly ordered structure. An amorphous solid is going to have them kind of arranged every which way, like this. This is an amorphous solid down here, whereas this would be a crystalline solid. Do you see the difference here? The crystalline solid, this one, is really highly ordered. You see a repeating pattern over and over and over again. This amorphous solid is all kind of jumbled up and weird, okay? Only molecular substances can form amorphous solids. Both of them can form crystalline and usually our solids are going to be crystalline, okay? Most of the time, I would say like 99% of the time, your substances will form a crystalline solid. But every once in a while, they are going to form an amorphous solid and have their molecules all jumbled up all weird. So our examples, and I want you to know these, our examples of amorphous solids are plastics, glass, and gels. Those are the only three I want you to know as far as amorphous solids. Everything else, we are going to say forms a crystalline solid. So the only time you're going to get amorphous is one of these things. But I do want you to know that they form amorphous solids. So like our beakers in lab, those are not a highly ordered structure. And a lot of people are surprised by that because it's easy to see through glass, right? And so usually they think of, okay, I can see through it. It must be structured in some way that allows it to have this property, right? But nope, it's got all of its molecules all jumbled up, all crazy. Kind of cool though. All right, we have another type of solid that we can have, and these are called atomic solids. Okay, and so these are for singular atoms. Okay, so if you have a singular atom, then you will have an atomic solid. And usually this is only when we have a metal. So this is a metallic crystalline solid. Okay, and it's going to be highly ordered three-dimensional array, but only of metal atoms. So this would be something like aluminum or maybe iron, right? This is going to be how those metals come together. And so we actually haven't talked about what happens if you have just a metal. We've talked about a metal and a nonmetal, that was ionic bonding. We've talked about all nonmetals, that was covalent bonding. But what if it was just metals, right? We haven't talked about that. Well, just metals is called metallic bonding. And so these are the forces that hold a solid metal together. So if I just like have a sheet of iron or a brick of lead, right? What's holding that together? And so the thing that's holding that together is metallic bonding. Metallic bonding is kind of weird, and we don't talk a lot about it in chemistry, except for this one chapter. So I'm not going to spend a lot of time on it, but I do think it's interesting. But essentially what happens is in metallic bonding, each metal atom basically shares its valence electrons with all of the other atoms in the solid. Okay? Think about that for a second. So our metal is going to share its valence electron with all of the other atoms. Not just the ones next to it, not the ones it's like quote unquote bonded to, right? But all of the metal atoms in the entire solid. And so we call this network or this array of our metals, we say that the electrons can move about as a sea of electrons. So all of the electrons can move throughout this entire solid. And so they kind of end up being a bunch of metal cations with the electrons kind of just floating around in the solid. So see, it's a little bit weird to think about, right? But the cool thing is, it's this whole free movement of the electrons moving around. That is why metals conduct electricity so well, is because they already have electrons kind of flowing. And that's what electricity is, flowing electrons. And so our metals have a bunch of cations with electrons floating around, so they can conduct electricity well because the electrons in the electricity just kind of jump from metal cation to metal cation and travel through the metal. Kind of cool. But what I want you to get out of this slide, other than metallic bonding is interesting and cool, is that if you see a singular element, just a metal, then we are going to say that's an atomic solid held together by metallic bonding. All right, another type of solid is a network solid. Network solids, I think, are really cool. In a network solid, all of the atoms, every single one, are connected by covalent bonds. And these covalent bonds are stronger than ionic bonds in a network solid. So let's think about this one. This is a diamond, right? We know diamonds are actually one of the hardest substances. You can use diamonds to cut a lot of things. They're not just pretty and rings and earrings and things like that, but they're actually really, really useful. And the reason for that is that diamonds have a really ordered structure, and it's all carbon, which is cool. So carbon, like we learned before, can make 4 bonds because it has 4 valence electrons, right? So carbon, its Lewis dot structure looks like this. And so carbon can attach to 4 other atoms. And this diamond just continually has carbon atoms that are attached to 4 other carbon atoms, and they make these really cool structures. Same thing here. This is graphite in your pencils. So when you're writing with your pencils, please, pet peeve of mine, don't say that you need more lead, right? Because it's not lead, it's actually graphite, right? Lead is a totally different element. Your graphite that's in your pencils and in your mechanical pencils is actually sheets of carbon, very, very thin sheets of carbon. So that's what it looks like here. So like this is a sheet of carbon, and this is a sheet of carbon, and this is a sheet of carbon. So when you're writing on your paper, like if you're taking notes right now, you are actually writing in sheets of carbon. And so these sheets of carbon, again, each carbon atom is attached to 4 other carbon atoms. And so these are network solids. All of the atoms in the whole structure are connected by covalent bonds. Alrighty, so here is a flowchart to help you determine the different type of solids. The first thing you should do is figure out, is it an element or a compound? Let's say it's a singular element. And then you need to ask yourself, is it a one element or is it molecular? So when I say, an atomic element, remember this is going to be like a metal. And when it says molecular, that means like your diatomics. Okay, so that would be Hofbrinkel. So that's really what this is talking about. When it says, is it atomic or is it molecular? It's essentially asking, is it a metal or is it a diatomic molecule? If it's just a metal, right, which is usually what happens, then you're going to get an atomic crystal held together by metallic bonding. It's very rare that this would be a nonmetal, but if you did, you would have an atomic crystal and solid held together by dispersion forces. But that's pretty uncommon. Usually you would end up, if you have a nonmetal, they are usually going to be a diatomic, and then you'll get a molecular crystal and solid held together by dispersion forces. So these are actually the same. If instead it was a compound, you need to ask yourself, is it ionic or is it molecular? If it's ionic, it's always going to be an ionic crystal and solid held together by ionic bonding. That's the only thing it can be. So if you come across an ionic compound, you're going to say it's an ionic compound held together by ionic bonds. Okay? If it's molecular, though, then you need to figure out, is it polar or is it nonpolar? Remember, the way to do that is to draw a Lewis structure. And then you're going to see, do my dipoles cancel out? If they all cancel, it'd be nonpolar. If they don't all cancel, then it would be polar. So let's say they did all cancel. Then you would get a molecular crystalline solid held together by dispersion forces because it's nonpolar. Okay, so all we've got are dispersion forces. If it's polar, you need to figure out, does it also have hydrogen bonds? If it has hydrogen bonds, right, fluorine, oxygen, nitrogen, remember, hydrogen bonds just want to have fun, then it would be a molecular crystalline solid held together by, and do you see it's got all of these forces? So we include all of the forces because it does have all of them. Most of the time, if it has one of these 3, we would say, oh, it has hydrogen bonding. That's true, and the reason we say that is because hydrogen bonding is the most important. But it also has dipole-dipole interactions, and it also has dispersion forces. So if it has hydrogen bonding, it'll have all of the other ones as well. If it doesn't have hydrogen bonding, then it just has, if it doesn't have hydrogen bonding and it's still polar, then it'll have dipole-dipole and dispersion. Okay? I know it's a lot. Get some practice. Use this flow chart to help you do the practice problems. Once you do some practice, I think you'll see it's not quite so bad, especially if you already feel really good about the intermolecular forces and the Lewis structures. Okay? Hopefully you're seeing that everything we do in this class ties together as we move forward. So if you're ever not understanding any bits and pieces, or maybe you don't understand one particular lecture, remember that you can always attend my office hours and get some more help. Or you can, go to SI sessions or go to Mesa. There are lots of ways for you to get help in this class, but make sure you're not having gaps in your knowledge because we use all of it moving forward. All right, I want you to go ahead and pause here and try this problem. I want you to figure out the type of crystalline solid each substance would form, and then figure out the intermolecular forces that hold that solid together. So you're doing two different things. What type of crystalline solid and what are the intermolecular forces? So go ahead, pause here, and then come back when you're ready to see the answers. Alrighty, let's go over this. So our first one is iron. Do you see how that's just one element? So anytime it's going to be a single element, it's either going to be a metallic solid or it's going to be a molecular solid. Here, iron is a metal. Therefore, it's going to make a metallic solid. Okay, like I said, that was our new type of bonding that we learned about today, was metallic bonding. So our intermolecular forces are going to be metallic bonding and dispersion forces. Remember, everything's got dispersion forces, so just always throw that in there. But the most important type of bonding for this one would be metallic bonding. So we have metallic solid and metallic bonding. All right, our next one. Do you see that calcium bromide is an ionic compound? So if it's an ionic compound, therefore, it's going to make an ionic solid. Okay? And again, it's going to be held together by ionic bonding because it's an ionic compound. And it also has dispersion forces. All right, next one. Do you see that iodine is a singular element? Even though there are two of them, right, it's a diatomic, do you see it's just iodine, right? This tells us that it's a molecular solid and it's actually an atomic molecular solid, which is kind of weird. But the molecular solid, this is going to be non-metal and it's held together by dispersion forces only. So like all of these had dispersion forces and something else, dispersion forces and something else. This one only has dispersion forces because it's nonpolar. And this is a molecular solid. All right, our last one is sulfur dichloride. So this is a molecular compound. Anytime you find a molecular compound, you're going to need to draw the Lewis structure because you need to figure out, is this polar or is it nonpolar? So again, this is a molecular compound, therefore it's going to make a molecular solid. Okay, but we need to draw the Lewis structure. So if we drew out the Lewis structure, we would find that sulfur has 6 valence electrons. And when we bond our chlorine to it, it's going to look like this. Remember, anytime we have oxygen or sulfur that's in the middle, we need to make sure that this is bent. Because remember, it's something with 2 lone pairs and 2 bonds. This is classified as bent. So you're going to want to make sure your shape looks bent. Because then when we draw our dipoles here, right, we are going to see that the dipoles don't cancel out. If we had mistakenly drawn this in a linear form, because we just, didn't remember, you would think that the dipoles did cancel. So be very, very careful. This molecule is bent, therefore our dipoles don't cancel, and it is polar. Okay, so since it's polar, it's held together by dipole-dipole interactions and also dispersion forces. Okay, I want to go over this one more time. So this is a metal, therefore it makes a metallic solid. This is an ionic compound, therefore it makes an ionic solid. This is a non-metal, right? And it's going to make a molecular solid. This is non-metals, makes a molecular solid. So your options for the type of solid that can form are only molecular, ionic, or metallic. Those are your 3 options, and that's it. As far as the intermolecular forces go, we talked about that a lot last time. The only thing that's really new is our metals are held together by metallic bonding. But otherwise, like an ionic compound held together by ionic bonding, this is a non-polar substance, so it's only dispersion. This is polar, so we get dipole-dipole interactions. Okay, so this is just drawing together a lot of different things that we've covered already in the course. Alrighty, this is actually the end of today's lecture. Kind of a short one for today, but like I said, it's drawing together a lot of different pieces that we've already worked on. So go ahead and get some practice on this by completing problem number 1 on the Chapter 7 lecture worksheet. Again, if you ever have any questions on anything, please feel free to reach out. I'm always happy to answer your questions and help you in any way that I can. Otherwise, I'll talk to you guys next time.